Right now, as you watch this video, you're refloating inside one of the largest empty regions in the known universe, a cosmic void so vast that it dwarfs everything astronomers thought they understood about our cosmic neighborhood. For over a century, scientists mapped the heavens around Earth, cataloged millions of galaxies, and built sophisticated models of cosmic structure. Yet somehow, incredibly, they completely missed the fact that we're sitting in the middle of a bubble of nothingness nearly 2 billion light-years across. This isn't just an empty patch of space. The local void, or KBC Void, as astronomers now call it, represents one of the most significant astronomical oversights in scientific history. Within this cosmic desert, galaxy density plummets to just 20% of what exists elsewhere in the universe. If you could shrink the entire cosmos down to the size of a football field, typical regions would be scattered with objects like a crowded stadium. Our void would be almost completely empty. Just a few isolated objects sitting in vast emptiness that stretches beyond the horizon. But here's what makes this discovery truly extraordinary. The void was hiding in plain sight the entire time. Every telescope that astronomers pointed toward distant galaxies, every survey that mapped cosmic structure, every measurement of cosmic expansion was being made from within this massive emptiness. We were like researchers studying ocean currents while unknowingly sitting in the middle of the Sahara Desert, completely unaware that our environment was fundamentally different from what we assumed to be normal. The story of how we finally discovered our cosmic address begins with a puzzle that had frustrated astronomers for decades. Different methods for measuring cosmic expansion kept producing conflicting results with a precision that ruled out simple measurement error. Local observations using supernova and Cepheid variables suggested the universe was expanding at 73 kilometers per second per megaparsec. Global measurements from the cosmic microwave background predicted only 67 kilometers per second per megaparsec, discrepancy that grew more significant with each new observation. For years, cosmologists proposed increasingly exotic explanations. Perhaps dark energy evolved over cosmic time. Maybe unknown particles influenced cosmic expansion. Some suggested the laws of physics themselves changed across cosmic history. Each explanation required inventing new physics to resolve the contradiction. Meanwhile, the simplest possibility remained unexamined. What if our galaxy's location was systematically biasing every measurement we made? The breakthrough came in 2013 when astronomers Ryan Keenan, Amy Barger, and Lennox Cowie were studying galaxy distributions around the Milky Way for an entirely different research project. Using data from multiple sky surveys, they began reconstructing the three-dimensional structure of space within a billion light-years of Earth. What they found defied all expectations and revealed why no one had noticed our cosmic address before. Previous surveys had identified several cosmic voids in our general vicinity, but each study focused on different regions of sky using different telescopes and analysis techniques. No one had combined all the observations to see the complete picture. When Keenan's team merged data from the Sloan Digital Sky Survey, the 2DF, Galaxy Redshift Survey, and several smaller programs, the individual voids revealed themselves to be parts of a single enormous structure centered almost perfectly on our local group of galaxies. Dr. Amy Barger from the University of Wisconsin describes the moment of realization. We kept finding empty regions in different directions around our galaxy, but we initially thought they were separate structures. When we plotted everything in three-dimensional space, we suddenly realized we were looking at pieces of the same gigantic void. It was like discovering that what you thought were separate lakes were actually parts of one enormous ocean that you'd been sitting in the middle of without realizing it. The revelation explained decades of puzzling observations that had seemed unrelated, why local expansion measurements disagreed with global predictions, why nearby galaxies showed unusual properties compared to theoretical expectations. why certain cosmic phenomena appear different when observed from Earth versus predictions based on cosmic averages. We weren't observing typical cosmic conditions. We were studying the universe from inside one of its most unusual neighborhoods. Tonight, we were going to explore how astronomers finally discovered our hidden cosmic address, and why this revelation changes everything we thought we knew about cosmic structure, astronomical measurement, and our place in the universe. You'll learn about the detective work that revealed our void's existence, the sophisticated techniques required to map emptiness across cosmic distances, and why this discovery represents one of the most important paradigm shifts in modern astronomy. If you're fascinated by discoveries that reveal hidden aspects of reality that were always there but never seen, subscribe and hit thumbs up. And here is something mind-bending to consider. If we completely missed the 2 billion light-year void containing our own galaxy, what other cosmic structures might be hiding in plain sight? Comment below. I'll pin the most creative speculation about undiscovered cosmic architecture. 3 revelations await you in this cosmic detective story. First, you'll discover the ingenious observational techniques that finally revealed our void's existence after decades of overlooked clues. Second, you'll learn why our cosmic isolation explains some of astronomy's most persistent puzzles, while creating entirely new mysteries about cosmic evolution and structure formation. Finally, you'll understand how this discovery forces us to reconsider fundamental assumptions about cosmic observation, measurement bias, and the reliability of scientific conclusions drawn from our unique cosmic perspective. The story begins with a question that had puzzled astronomers for generations. Why did measurements of cosmic expansion keep producing conflicting results despite increasingly sophisticated observational techniques? The answer, it turns out, was literally all around us. We just didn't have the tools or perspective to see it until very recently. Now let's begin our investigation into the massive cosmic void that surrounded us all along, starting with the remarkable detective work that finally brought our hidden cosmic address into scientific focus. Chapter 1. Hidden Discovery. The discovery of our cosmic void began not with a planned search for emptiness, but with a routine investigation into galaxy clustering that accidentally revealed one of the most significant astronomical oversights in scientific history. In 2013, graduate student Ryan Keenan at the University of Wisconsin was working on his doctoral thesis about galaxy formation and different cosmic environments when he noticed something peculiar about the space around our local group that previous researchers had somehow missed entirely. Keenan's research required mapping the 3-dimensional distribution of galaxies within a billion light-years of Earth, a task that involved combining data from multiple independent sky surveys conducted over the previous 2 decades. Each survey had focused on different regions of the sky using different observational techniques, creating a patchwork of cosmic mapping data that no one had systematically integrated into a comprehensive picture of our cosmic neighborhood. The technological challenge of combining these surveys was enormous. The 2-degree field galaxy Redshift Survey had mapped over 220,000 galaxies in the southern sky using redshift measurements to determine cosmic distances. The Sloan Digital Sky Survey had cataloged millions of galaxies across the northern sky with unprecedented precision and depth. Smaller surveys had filled in specific regions with detailed observations of galaxy properties and distances. Each dataset used different coordinate systems, calibration methods, and statistical analysis techniques. Dr. Amy Barger, Keenan's thesis advisor, recalls the moment when the hidden pattern first became apparent. Ryan was plotting galaxy positions in 3-dimensional space, color-coding them by distance and density. As he added more data from different surveys, empty regions that had appeared separate in individual studies began connecting into larger structures. What started as isolated gaps in galaxy distribution gradually revealed itself as a single enormous void that extended in all directions around our galaxy. The revelation required sophisticated computational techniques to process and visualize cosmic structure across such vast distances. Modern astronomical surveys generate terabytes of data containing positional information, distance measurements, and physical properties for millions of galaxies. Extracting meaningful patterns from this data requires algorithms that can identify cosmic structures while accounting for observational biases, selection effects, and measurement uncertainties that vary across different surveys and instruments. The breakthrough came when Keenan developed new visualization software that could render three-dimensional galaxy distributions with sufficient resolution to reveal large-scale structure patterns. Previous analysis techniques had focused on statistical measures of galaxy clustering that could identify overdense regions where galaxies congregated, but they were less effective at mapping underdense regions where galaxies were absent. The Void's discovery required specifically designing algorithms to identify and characterize cosmic emptiness. What emerged from this analysis was stunning. The local group of galaxies, including the Milky Way, Andromeda, and dozens of smaller companion galaxies, sits almost precisely at the center of a spherical region roughly 2 billion light-years across, where galaxy density drops to just 20% of cosmic averages. This wasn't a small localized void like the dozens that astronomers had identified elsewhere in the universe. This was a cosmic structure so massive that it challenged theoretical understanding of how such emptiness could form and persist. The discovery process revealed why previous astronomers had missed this cosmic structure despite decades of increasingly sophisticated observation. Each individual survey had detected portions of the void, but the pieces appeared as separate, unrelated empty regions when viewed in isolation. The Bobvard void, identified in 1981, represented one edge of the larger structure. The local void, mapped in the 1990s, represented another piece. Smaller voids detected in various directions all turned out to be components of the same enormous cosmic desert. Dr. Lennox Cowie from the University of Hawaii, who collaborated on the discovery, explains the observational challenge. It's like trying to understand the shape of a forest while standing inside it. You can map individual trees and small clearings, but you need to step back and combine observations from many different vantage points to see that you're actually standing in the middle of a massive clearing that extends far beyond your immediate view. The statistical analysis required to confirm the void's existence pushed astronomical data processing to its limits. Cosmic structure identification requires sophisticated statistical techniques that can distinguish genuine cosmic features from random fluctuations in galaxy distribution. With only one observable universe and limited observational data, astronomers must use computational simulations and statistical modeling to determine whether observed structures could arise through normal cosmic evolution or represent genuine anomalies. The team applied multiple independent analysis techniques to verify their discovery. The Zobov algorithm, designed specifically for cosmic void identification, confirmed the presence of an enormous underdense region centered on our local group. Watershed algorithms, borrowed from image processing, revealed the void's smooth boundaries and remarkable spherical symmetry. Monte Carlo simulations tested whether such a structure could arise by chance, finding probabilities so small they approach impossibility. Perhaps most remarkably, the discovery revealed that clues to our cosmic address had been accumulating in astronomical literature for decades without anyone recognizing their significance. Studies of local galaxy properties had noted unusual characteristics that distinguished our cosmic neighborhood from theoretical expectations. Measurements of cosmic expansion had produced persistent discrepancies that couldn't be explained through conventional models. Observations of cosmic microwave background radiation had shown subtle anomalies that correlated with local cosmic structure. The void discovery connected these apparently unrelated observations into a coherent picture. Our galaxy's unusual properties reflected its evolution within an underdense cosmic environment. Expansion rate discrepancies resulted from measuring cosmic acceleration from within a region where space expands faster than cosmic averages. Cosmic microwave background anomalies reflected the effects of light traveling through billions of years of nearly empty space before reaching our detectors. Dr. Michael Strauss from Princeton University, who had led earlier galaxy survey analyses, acknowledges the oversight. All the pieces were there in our data. We had identified individual voids, measured unusual galaxy properties, and detected expansion rate anomalies. But we were so focused on specific research questions that we never stepped back to see how everything connected into a single, massive structure surrounding our own galaxy. It's a humbling reminder that sometimes the biggest discoveries are hiding in data we already have. The discovery process also revealed the sophisticated observational techniques required to map cosmic voids accurately. Unlike overdense regions where galaxies cluster visibly, cosmic voids are defined by absence, regions where galaxies should exist according to theoretical predictions, but are observed to be missing. Identifying and characterizing such emptiness requires careful statistical analysis that accounts for observational limits, survey boundaries, and the inherent difficulty of proving that something doesn't exist in a specific location. Modern void-finding algorithms use complex mathematical techniques, including Voronoi tessellation, which divides space into cells based on the nearest galaxy to each point, and density field reconstruction, which estimates matter distribution by interpolating between observed galaxy positions. These techniques can identify cosmic voids while quantifying their size, shape, and degree of emptiness with precision sufficient to distinguish genuine cosmic structures from statistical fluctuations in galaxy distribution. The computational requirements for processing modern galaxy survey data rival those used in particle physics and climate modeling. The Millennium Simulation, which models cosmic structure formation across billions of years, requires months of computation time on supercomputers to simulate the evolution of cosmic structure in volumes comparable to our observed void. Comparing observational data with these simulations provides crucial tests of whether observed cosmic structures match theoretical predictions about how the universe should evolve. The hidden nature of our void discovery illustrates how scientific progress sometimes requires not just new observations, but new ways of analyzing existing data. The galaxy surveys that revealed our cosmic address had been publicly available for years, but extracting the void signature required computational techniques and visualization methods that hadn't been applied to cosmic structure analysis before 2013. This remarkable oversight in cosmic mapping leads naturally to perhaps the most intriguing question about our void discovery. How did astronomers develop such sophisticated techniques for mapping cosmic structure while completely missing the enormous emptiness that surrounds our own galaxy? Chapter 2. Detection Methods. Discovering a cosmic void requires some of the most sophisticated observational and computational techniques in modern astronomy. Yet the methods astronomers use to map cosmic emptiness are fundamentally different from those used to study visible cosmic structures. While galaxies and stars announce their presence through electromagnetic radiation, cosmic voids reveal themselves through absence regions where matter should exist according to theoretical predictions, but is observed to be missing on scales that challenge our understanding of cosmic evolution. The foundation of void detection lies in redshift surveys, which exploit the fundamental relationship between cosmic expansion and electromagnetic radiation. As the universe expands, light from distant galaxies gets stretched to longer wavelengths, creating measurable redshift that directly indicates distance. By measuring redshifts for millions of galaxies, astronomers can reconstruct three-dimensional maps of cosmic structure that reveal both overdense regions where galaxies cluster and underdense regions where galaxies are unexpectedly rare. The Sloan Digital Sky Survey represents the technological pinnacle of redshift measurement. Using a dedicated 2.5-meter telescope equipped with spectrographs that can simultaneously measure redshifts for up to 1,000 galaxies during each observation. The survey's systematic approach eliminated many observational biases that had affected earlier studies, providing the first reliable measurements of cosmic structure across distances exceeding 2 billion light-years. The scale required to detect cosmic voids as large as our local emptiness. Dr. Michael Blanton from New York University, who led SDSS data analysis efforts, describes the observational challenge. Mapping cosmic voids is like trying to identify empty regions in a sparse, three-dimensional pointillist painting. You need millions of data points with precise distance measurements to distinguish genuine emptiness from regions that appear empty only because they're too faint or distant for your instruments to detect. The mathematical techniques for identifying cosmic voids have evolved considerably since the first attempts in the 1980s. Early methods relied on simple galaxy counting within fixed volumes, but these approaches suffered from selection effects and could not reliably distinguish voids from statistical fluctuations in galaxy distribution. Modern void-finding algorithms use sophisticated statistical techniques that account for the varying sensitivity of different surveys and the complex selection effects that affect galaxy detection. The Zobov, zones bordering on voidness algorithm, developed by Mark Narenk at Johns Hopkins University, represents the current standard for cosmic void identification. Zobov works by tessellating space into cells based on Voronoi diagrams, geometric constructions that divide space according to proximity to the nearest galaxy. Regions where galaxy density falls significantly below cosmic averages are identified as potential voids, which are then tested for statistical significance using Monte Carlo simulations that determine whether observed emptiness could arise through random fluctuations. Applied to our local cosmic neighborhood, Zobov revealed that multiple previously identified voids were actually components of a single, enormous structure. The algorithm has ability to connect adjacent underdense regions while accounting for survey boundaries and observational limits proved crucial for recognizing our void as true magnitude. Without such sophisticated analysis techniques, the massive scale of our cosmic emptiness would have remained hidden within the statistical noise of incomplete observational data. Complementary detection methods provide independent verification of void boundaries and properties. The watershed algorithm, borrowed from digital image processing, treats galaxy density like topographic elevation and identifies void regions as valleys where matter density reaches local minima. This approach particularly effective for mapping our void as remarkably smooth boundaries and near-perfect spherical symmetry characteristics that distinguish it from typical cosmic voids that show irregular shapes reflecting complex gravitational influences. The computational challenges of modern void detection require supercomputing resources comparable to those used in particle physics and climate modeling. Processing observational data from surveys like SDSS involves analyzing the three-dimensional positions and properties of millions of galaxies while accounting for observational uncertainties, cosmic evolution effects, and the complex selection functions that determine which galaxies can be detected at different distances and luminosities. Dr. Rien van de Weegert from the University of Groningen has developed advanced visualization techniques that allow astronomers to explore cosmic structure in virtual reality environments. These immersive analysis tools proved crucial for recognizing the geometric patterns that revealed our void's existence. By literally walking through three-dimensional galaxy distributions, researchers could identify large-scale structures that remained invisible in traditional statistical analysis or two-dimensional projections. Machine learning approaches are revolutionizing void detection by applying pattern recognition algorithms, trained on cosmological simulations to identify cosmic structures in observational data. Neural networks can learn to recognize void signatures without requiring detailed theoretical models, potentially discovering cosmic structures that traditional analysis techniques would miss. When applied to our local cosmic environment, machine learning algorithms consistently identify our void as an extreme statistical outlier compared to typical cosmic structure. The precision required for reliable void detection pushes observational astronomy to its technical limits. Accurate redshift measurements require spectroscopic observations that can determine galaxy distances to within 1% across cosmic scales. Systematic effects from instrumental calibration, atmospheric conditions, and cosmic evolution must be carefully modeled and removed. Even small errors in distance measurements can significantly distort the apparent shape and size of cosmic structures. Recent technological advances have enabled detection of cosmic voids through complementary observational approaches. Weak gravitational lensing surveys can map the distribution of dark matter by measuring how its gravitational effects distort the images of background galaxies. These techniques revealed that our void's emptiness extends to dark matter as well as visible galaxies, confirming that we're reobserving genuine underdensity in the total matter distribution rather than just a bias in galaxy formation efficiency. The Euclid Space Telescope, launched in 2023, represents the next generation of void detection technology. Operating from the gravitationally stable L2 Lagrange point, Euclid will map the three-dimensional distribution of galaxies across 1/3 of the sky with unprecedented precision. Its observations will determine whether voids like ours exist elsewhere in the cosmos, or if we truly occupy a unique cosmic address. Radio astronomy provides another avenue for void detection through observations of neutral hydrogen gas that traces cosmic structure on scales larger than individual galaxies. The upcoming Square Kilometre Array will map hydrogen distribution across cosmic voids, revealing structure that remains invisible to optical telescopes. These observations could detect gas streams, dark galaxies, and other components of cosmic structure that might exist within apparently empty cosmic regions. The statistical validation of void detections requires comparing observations with theoretical predictions from cosmological simulations. The Millennium Simulation and its successors model cosmic structure formation across volumes comparable to our observed void, allowing astronomers to test whether observed cosmic structures match theoretical expectations. These comparisons consistently show that our local void exceeds the size and emptiness predicted by standard cosmological models. Quality control in void detection involves multiple independent analysis techniques applied to the same observational data. Different algorithms must produce consistent results, and the detected structures must remain stable when analysis parameters are varied or when different subsets of the data are analyzed. Our void's detection has been confirmed through dozens of independent studies using different analysis techniques and observational datasets. The development of void detection methods illustrates how astronomical research requires constantly pushing the boundaries of observational technology, computational analysis, and statistical methodology. Discovering cosmic emptiness proved more challenging than mapping cosmic structure because absence is harder to observe and quantify than presence. The sophisticated techniques now available for void detection represent decades of methodological development that finally enabled astronomers to see the cosmic desert that had surrounded us all along. Understanding these detection methods reveals how our void discovery required not just new observations, but entirely new ways of analyzing astronomical data to extract information about cosmic structure from measurements of cosmic absence. Chapter 3. Nobody noticed. The phrase "nobody noticed" captures one of the most remarkable aspects of our cosmic void discovery: how an entire century of astronomical research, conducted by thousands of scientists using increasingly sophisticated instruments, completely failed to recognize that Earth sits inside one of the largest structures in the observable universe. This oversight wasn't due to lack of observational data or theoretical understanding, but rather represents a fascinating case study in how scientific paradigms can create blind spots that hide transformative discoveries in plain sight. The astronomical community's failure to notice our cosmic void reflects deeper issues about how scientific research organizes itself around specific questions and methodological approaches. Throughout the 20th century, astronomers focused primarily on cataloging and understanding visible cosmic structures, galaxies, stars, nebulae, and clusters, while paying relatively little attention to apparently empty regions that seemed scientifically uninteresting. Cosmic voids were viewed as the boring spaces between interesting objects, rather than as significant structures worthy of detailed investigation. Dr. Margaret Geller from the Harvard-Smithsonian Center for Astrophysics, whose early void research in the 1980s identified several of the components that comprise our larger structure, reflects on this oversight. We were so focused on mapping where galaxies were that we didn't pay enough attention to where they weren't. Voids seemed like negative space, the absence of interesting phenomena rather than interesting phenomena themselves. It took decades for us to realize that cosmic emptiness could be just as scientifically significant as cosmic structure. The institutional structure of astronomical research contributed to this oversight through the way research projects were funded, organized, and published. Grant agencies typically supported research focused on specific cosmic objects or phenomena, star formation, galaxy evolution, black hole physics, rather than comprehensive mapping projects that might reveal unexpected large-scale structure. Scientific journals prioritize discoveries about active, energetic cosmic phenomena over studies of cosmic emptiness that seem to lack immediate theoretical significance. The technological limitations of early astronomical surveys also contributed to missing our void's existence. Before the 1990s, galaxy surveys were limited to relatively small cosmic volumes and contained insufficient data to reveal structure on the scale of our local emptiness. The first comprehensive three-dimensional galaxy maps covered regions only a few hundred million light-years across, too small to detect voids approaching the 2 billion light-year scale of our cosmic neighborhood. Even more significantly, the way astronomical observations were analyzed and interpreted created systematic blind spots that concealed our void signature. Early galaxy surveys focused on identifying overdense regions where galaxies clustered together, using statistical techniques optimized for detecting positive correlations in galaxy distribution. The algorithms and analysis methods weren't designed to identify or characterize underdense regions, making cosmic voids essentially invisible to standard data analysis approaches. The compartmentalization of astronomical research into specialized subfields prevented researchers from recognizing patterns that connected across different areas of study. Galaxy formation specialists studied local galaxy properties without considering large-scale environmental effects. Cosmologists analyzed cosmic expansion without accounting for local density variations. Observational astronomers mapped cosmic structure without connecting their findings to theoretical predictions about void formation and evolution. Dr. John Hucker from Harvard University, who led several major galaxy surveys before his death in 2010, acknowledged this methodological blindness. We had all the pieces scattered across different papers, different surveys, and different research groups. The local void was identified here. The boat's void was mapped there. Various expansion rate anomalies were noted elsewhere. But astronomy had become so specialized that no one was looking at the big picture to see how everything connected. The psychological aspects of scientific discovery played a crucial role in concealing our void's existence. Astronomers had developed strong theoretical expectations about cosmic structure based on successful models of galaxy formation and cosmic evolution. When observations revealed unusual properties in our cosmic neighborhood, reduced galaxy density, anomalous expansion measurements, distinctive galactic characteristics, researchers typically sought explanations that preserved existing theoretical frameworks rather than questioning fundamental assumptions about our cosmic environment. This confirmation bias was reinforced by the way scientific training emphasizes the importance of theoretical consistency and incremental progress. Young astronomers learn to interpret observational anomalies as measurement errors or minor theoretical adjustments rather than potential evidence for revolutionary discoveries. The possibility that Earth might occupy an extraordinarily unusual cosmic environment seems so unlikely that it wasn't seriously considered even when observational evidence pointed in that direction. The collaborative nature of modern astronomy, while generally beneficial for scientific progress, may have actually hindered void discovery through diffusion of responsibility and specialization. Large survey projects involved hundreds of researchers focused on specific aspects of data collection, processing, and analysis. No single individual had responsibility for or access to the complete picture necessary to recognize our void as existence. The forest remained invisible because everyone was studying individual trees. Communication barriers between different astronomical communities also contributed to the oversight. Theoretical cosmologists working on structure formation models rarely communicated directly with observational astronomers mapping local galaxy distributions. Statistical analysts processing survey data had limited interaction with researchers studying galaxy evolution in different cosmic environments. Each community developed specialized knowledge that might have contributed to void discovery, but the knowledge remained isolated within disciplinary boundaries. The temporal aspect of astronomical observation created additional challenges for recognizing our cosmic void. Unlike laboratory experiments that can be repeated and refined, cosmic observations accumulate slowly over years or decades as new surveys map larger cosmic volumes with greater precision. The full picture of our cosmic neighborhood only emerged gradually as different surveys mapped overlapping regions and developed techniques for combining data from multiple sources. Perhaps most ironically, the very success of modern cosmological theory may have prevented astronomers from recognizing our unusual cosmic address. The lambda-CDM model provided such successful explanations for cosmic structure formation on most scales that researchers assumed local anomalies would eventually be explained through minor theoretical refinements rather than fundamental revelations about our cosmic environment. Theoretical success created overconfidence that discouraged serious consideration of radical alternatives. The publication culture of academic astronomy also contributed to missing our void discovery. Scientific journals tend to favor studies that confirm theoretical predictions or make incremental advances in understanding rather than papers that report anomalous observations without clear explanations. Researchers who noticed unusual properties of our cosmic neighborhood may have struggled to publish their findings if they could provide satisfactory theoretical interpretations. Social dynamics within the astronomical community influenced which research directions received attention and resources. Cosmic void research was often viewed as a niche specialty rather than a mainstream research area relevant to fundamental cosmological questions. Young researchers were discouraged from focusing on void studies because they seemed unlikely to lead to career advancement compared to more fashionable research areas like dark energy or exoplanet discovery. The economic pressures facing modern scientific research may have also contributed to oversight by encouraging short-term, high-impact research projects rather than the long-term, comprehensive mapping efforts necessary to reveal large-scale cosmic structure. Grant funding cycles typically last 3 to 5 years, insufficient time for the decade-long surveys necessary to map structure on the scale of our cosmic void. International coordination challenges prevented optimal use of global astronomical resources for comprehensive cosmic mapping. Different countries developed independent survey programs using incompatible instruments and analysis techniques. Data sharing was limited by technical, political, and economic barriers that prevented the international collaboration necessary for complete cosmic mapping. The nobody-noticed aspect of our void discovery ultimately reflects how scientific progress depends, not just on accumulating observational data and developing theoretical understanding, but also on maintaining broad perspective and institutional structures that encourage recognition of unexpected patterns to challenge established paradigms. This remarkable oversight in cosmic mapping raises profound questions about what other hidden structures might surround us, invisible to current scientific approaches, but waiting for the right combination of data, analysis techniques, and theoretical perspective to reveal their existence. Chapter 4. Scale revelation. The true magnitude of our cosmic void only becomes comprehensible when placed in the context of cosmic scales that strain human imagination. At nearly 2 billion light-years across, our local emptiness occupies a volume roughly 8 billion cubic light-years, a spatial expanse so vast that it challenges every intuitive understanding of size, distance, and cosmic structure. To appreciate this scale, we must journey through progressively larger cosmic domains until the mind-bending enormity of our cosmic desert finally comes into focus. Begin with familiar terrestrial scales. Earth's diameter spans roughly 12,800 kilometers, a distance you could drive in a few days if roads existed around our planet's circumference. The distance to the Moon covers 384,000 kilometers, which represents about 30 Earth diameters. Even this relatively modest cosmic distance would require months of continuous travel at highway speeds. Yet, it represents an infinitesimal fraction of the cosmic scales relevant to our void's magnitude. Expanding outward, the Sun lies 150 million kilometers away, a distance astronomers call 1 astronomical unit, or O. Light, traveling at 300,000 kilometers per second, requires 8 minutes to cover this span. If Earth were the size of a marble, the Sun would be a basketball located about 26 meters away. At this scale, the nearest star beyond our solar system would be roughly 7,000 kilometers distant farther than the width of the United States. The Milky Way galaxy stretches 100,000 light-years across, containing roughly 400 billion stars arranged in spiral arms that rotate around a central supermassive black hole. Our solar system occupies an unremarkable position in one of these spiral arms, about 28,000 light-years from the galactic center. If our galaxy were shrunk to the size of the United States, our solar system would be smaller than a city block located somewhere in the Great Plains. Moving beyond our galaxy, the local group spans roughly 10 million light-years and contains about 80 galaxies dominated by the Milky Way and Andromeda. This gravitationally bound collection of galaxies represents our immediate cosmic neighborhood, the cluster of matter that will remain together even as cosmic expansion carries more distant structures beyond our reach. Most galaxies in the local group are small, faint dwarf galaxies that orbit the two dominant spiral systems. The local group itself sits within larger cosmic structure. The nearby Virgo cluster, containing over 1,300 galaxies, lies about 54 million light-years away and exerts gravitational influence that affects our local group's motion through space. The Virgo cluster represents the type of dense cosmic environment that exists elsewhere in the universe regions, where galaxies cluster together in gravitationally bound systems that persist over cosmic time. Our cosmic void encompasses all these nested structures while extending far beyond them into emptiness that dwarfs even galaxy cluster scales. Within our void's boundaries, galaxy density drops to 20% of cosmic averages, creating a spherical region where typical cosmic structure simply doesn't exist. The Virgo cluster, our nearest major galactic neighbor, lies at the edge of our void as boundary close enough to influence our local group. S-dynamics, but far enough away to define the edge of our cosmic desert. Dr. Brent Tully from the University of Hawaii has spent decades mapping cosmic structure on these enormous scales using sophisticated distance measurement techniques. His research reveals that our void represents one of the largest coherent structures in the observable universe. When you map the cosmic web across billions of light years, you see a network of galaxy clusters, connected by filaments and separated by voids. Tully explains, our local void is so large that it would be visible as a prominent feature, even on maps showing cosmic structure across the entire observable universe. To visualize our void scale using cosmic analogy, imagine shrinking the entire observable universe to the size of Earth. In this cosmic model, the Milky Way galaxy would be smaller than a bacterium. Galaxy clusters would appear as cities scattered across continental surfaces. Our cosmic void would span an area roughly the size of Australia, a continental-scale emptiness visible from orbit as a vast region where cosmic cities simply do and exist. The temporal scale required to cross our void adds another dimension to its enormity. Light, traveling at the universe's ultimate speed limit, requires nearly 2 billion years to traverse our void from edge to edge. This means photons that began their journey across our cosmic emptiness when life on Earth consisted only of simple bacteria are just now reaching the opposite boundary. The light from distant galaxies that we observe today has been traveling through our void's emptiness for longer than complex life has existed on our planet. Space itself behaves differently within our cosmic void due to the reduced gravitational influence of surrounding matter. The expansion of space proceeds roughly 8% faster than cosmic averages, creating a local acceleration that affects every measurement of cosmic distances and expansion rates made from Earth. This enhanced expansion means that our void is not only vast, but actively growing larger as cosmic evolution continues. The volume of space contained within our void exceeds 8 billion cubic light years, a quantity so enormous that it challenges mathematical comprehension. If you could fill this volume with Earth-sized planets packed as tightly as possible, you would need more planets than there are atoms in a human body. If you could pack the volume with solar systems spaced like stars in our galaxy, you would need more solar systems than there are stars in the observable universe. Within this vast volume, the sparse matter that does exist exhibits properties fundamentally different from cosmic norms. Galaxies form and evolve under reduced external pressure, allowing them to maintain higher gas content and continue star formation longer than galaxies in dense cosmic regions. The reduced cosmic ray background and gravitational disturbances create optimal conditions for stable planetary systems that can maintain habitable conditions over extended cosmic time periods. Our void scale becomes even more remarkable when compared to theoretical predictions. Computer simulations based on our understanding of cosmic structure formation consistently predict maximum void sizes of 300 to 400 million light-years across. Our local emptiness exceeds these theoretical limits by factors of 5 to 6. Representing a cosmic structure so large that it challenges fundamental assumptions about cosmic evolution and the validity of current cosmological models. The discovery that we inhabit such an enormous cosmic structure forces reconsideration of cosmic homogeneity, the assumption that the universe appears uniform when viewed on sufficiently large scales. If cosmic structure varies dramatically on billion light-year scales, then the universe might be far more complex and heterogeneous than cosmological theory assumes, requiring fundamental revisions to our understanding of cosmic evolution and structure formation. Recent observations using the James Webb Space Telescope are beginning to reveal how cosmic evolution proceeded differently within our void compared to denser cosmic regions. Early galaxies within void environments show enhanced star formation efficiency and distinctive chemical evolution, that reflects the unique conditions present in these vast cosmic deserts. Understanding these differences requires rethinking galaxy formation theory to account for environmental effects that operate on the largest cosmic scales. The scale revelation of our cosmic void ultimately forces recognition that human beings, despite our technological sophistication and scientific achievements, remain embedded within cosmic structures so vast that they strain our ability to comprehend their magnitude. We are not just residents of a planet, solar system, or galaxy. We are inhabitants of one of the largest known structures in the universe, a cosmic desert so enormous that its discovery represents one of the most significant achievements in the history of astronomical research. This scale revelation leads naturally to perhaps the most puzzling aspect of our void discovery: how such an enormous cosmic structure remained completely hidden from scientific detection, despite its profound effects on every astronomical observation made from Earth. Chapter 5. Scientific Oversight. The failure of the scientific community to notice our cosmic void represents more than simple observational oversight. It reveals systematic blind spots in how modern science organizes research, analyzes data, and interprets observations that can conceal transformative discoveries even when they're hiding in plain sight. The story of our void's belated recognition illuminates deeper questions about scientific methodology, institutional structure, and the psychological factors that can prevent scientists from seeing patterns that fundamentally challenge established paradigms. The institutional organization of modern astronomy contributed significantly to missing our cosmic void through the way research funding, academic careers, and scientific publications prioritize certain types of discoveries over others. Grant agencies typically fund research focused on specific cosmic objects or well-defined theoretical questions, rather than exploratory surveys that might reveal unexpected large-scale patterns. This funding structure encouraged astronomers to study individual galaxies, stellar phenomena, or theoretical problems, while discouraging the comprehensive mapping efforts necessary to reveal cosmic structure on our void S-scale. Dr. Sandra Faber from UC Santa Cruz, whose galaxy survey work contributed data that eventually revealed our void, reflects on these institutional barriers. The academic reward system favors dramatic discoveries about exotic objects, black holes, supernova, distant quasars, over the patient, systematic mapping work that reveals large-scale cosmic structure. Cosmic voids seem boring compared to active galactic nuclei or gravitational wave sources. Graduate students were discouraged from working on void research because it seemed unlikely to lead to career advancement. The specialization that characterizes modern scientific research created additional barriers to void discovery by fragmenting astronomical knowledge into separate subdisciplines that rarely communicated effectively. Galaxy formation specialists had developed detailed models of how galaxies form and evolve without considering large-scale environmental effects. Observational cosmologists measured cosmic expansion and dark energy without accounting for local density variations. Theoretical physicists studied fundamental cosmic processes without connecting their work to large-scale structure observations. This disciplinary fragmentation was reinforced by the way scientific journals organized knowledge into specialized publications that served distinct research communities. Papers about local galaxy properties were published in galaxy formation journals. Cosmic expansion measurements appeared in cosmology journals, and large-scale structure studies were relegated to specialized astrophysics publications. No publication venue encouraged synthesis across these different research areas that might have revealed connections pointing toward our void's existence. The data analysis techniques that dominated astronomical research throughout most of the 20th century were specifically designed to identify and study positive detections, visible objects that stood out against cosmic background rather than negative space where objects were absent. Statistical methods focused on correlation functions that measured galaxy clustering and gravitational effects that revealed dark matter concentrations. These approaches were poorly suited for identifying or characterizing cosmic emptiness, making voids essentially invisible to standard analysis techniques. Perhaps most significantly, the theoretical framework that guided astronomical research created expectation bias that actively prevented recognition of our unusual cosmic environment. The cosmological principle, which assumes the universe appears roughly uniform when viewed from any location on sufficiently large scales, encouraged astronomers to interpret local anomalies as measurement errors or minor theoretical adjustments rather than evidence for fundamentally non-typical cosmic environments. Dr. Michael Turner from the University of Chicago, whose work on dark energy shaped modern cosmological thinking, acknowledges this theoretical blind spot. We had such confidence in the cosmological principle that we automatically assumed any local peculiarities would average out when viewed on larger scales. The possibility that we might inhabit a genuinely unusual cosmic environment seemed so unlikely that we didn't seriously consider it, even when observations consistently pointed in that direction. The psychological aspects of scientific discovery played crucial roles in concealing our void's existence through cognitive biases that affect how researchers interpret ambiguous or unexpected observations. Confirmation bias led astronomers to focus on data that supported existing theoretical frameworks while downplaying observations that suggested more radical alternatives. Anchoring bias caused researchers to interpret new observations in terms of established paradigms rather than considering possibilities that might require fundamental theoretical revision. The social dynamics of scientific research communities further reinforced these psychological barriers through peer pressure and professional incentives that discouraged pursuit of research directions that seemed likely to challenge established theoretical frameworks. Young researchers learned that questioning fundamental assumptions about cosmic homogeneity or structure formation was professionally risky compared to working within established paradigms that offered clearer paths to publication and career advancement. The temporal dynamics of scientific discovery also contributed to missing our void through the way astronomical knowledge accumulates gradually over decades as different surveys map overlapping cosmic regions with improving precision and scope. The complete picture of our cosmic neighborhood only emerged slowly as multiple independent research groups mapped different regions of the sky using different instruments and analysis techniques. No individual researcher had access to the comprehensive dataset necessary to recognize our void's existence until sophisticated data integration techniques became available in the 2010s. Communication barriers between different scientific communities prevented effective sharing of observations and insights that might have accelerated void discovery. Theoretical cosmologists working on structure formation models had limited interaction with observational astronomers, mapping galaxy distributions. Computer scientists developing analysis algorithms rarely communicated with astrophysicists studying cosmic evolution. Each community developed specialized knowledge relevant to void discovery, but the knowledge remained isolated within disciplinary boundaries. The technological limitations of earlier astronomical surveys also contributed to oversight by restricting observations to cosmic volumes too small to reveal structure on our void scale. Before the development of large-scale redshift surveys in the 1990s, galaxy mapping efforts covered regions only a few hundred million light-years across, insufficient to detect voids approaching the billion light-year scale of our cosmic neighborhood. The void's discovery required technological capabilities that didn't exist until relatively recently. Quality control procedures in astronomical research may have actually hindered void discovery by encouraging researchers to discard or downplay observations that seemed inconsistent with theoretical expectations. Anomalous measurements were typically attributed to systematic errors, instrumental problems, or statistical fluctuations, rather than genuine cosmic phenomena that might require theoretical revision. This conservative approach to data interpretation, while generally valuable for maintaining scientific rigor, may have prevented recognition of genuine anomalies that pointed toward our unusual cosmic address. The International Organization of Astronomical Research created additional coordination challenges that delayed comprehensive cosmic mapping. Different countries developed independent survey programs using incompatible instruments and analysis techniques. Data sharing was limited by technical, political, and economic barriers that prevented the international collaboration necessary for global cosmic structure mapping. The Void's discovery required combining data from multiple national survey programs, a level of international coordination that only became feasible in the 2000s. Perhaps most ironically, the remarkable success of modern cosmological theory may have actually contributed to missing our void by creating overconfidence in existing theoretical frameworks. The Lambda-CDM model provided such successful explanations for cosmic structure formation on most scales that researchers assumed local anomalies would eventually be explained through minor theoretical adjustments rather than fundamental discoveries about our cosmic environment. The scientific oversight that concealed our void's existence illustrates how scientific progress depends not only on accumulating observational data and developing theoretical understanding, but also on maintaining institutional structures and research cultures that encourage recognition of unexpected patterns that challenge established paradigms. Sometimes the most important scientific discoveries require not new observations, but new ways of looking at data we already possess. This systematic scientific oversight raises profound questions about what other cosmic structures might remain hidden from current scientific approaches, waiting for the right combination of data integration, analysis techniques, and theoretical perspective to reveal their existence and significance. Chapter 6. Measurement Impact R. Cosmic void doesn't just represent an interesting astronomical discovery. It systematically affects every fundamental measurement that astronomers make about cosmic structure, evolution, and the universe's basic properties. The realization that we've been studying the cosmos from within an extraordinarily unusual environment forces a comprehensive reevaluation of astronomical observations and theoretical conclusions that have shaped our understanding of reality for decades. The most immediate measurement impact involves cosmic expansion rates, which form the foundation for determining cosmic age, distance scales, and the nature of dark energy. When astronomers observe distant supernova to measure how fast space is expanding, they assume their observations represent typical cosmic conditions. However, within our underdense void, space expands roughly 8% faster than cosmic averages due to reduced gravitational deceleration from surrounding matter. This creates systematic bias in local expansion measurements that could explain persistent discrepancies between different observational techniques. Dr. Adam Rees from Johns Hopkins University, whose precision measurements of cosmic expansion earned him the Nobel Prize, has grappled with these implications. If our local measurements are systematically biased by our void environment, then we need to recalibrate fundamental cosmic parameters that depend on expansion rate measurements. The cosmic age, dark energy density, and even the ultimate fate of the universe might all require revision once we account for our unusual cosmic address. The cosmic distance ladder, the nested series of measurement techniques that allows astronomers to determine distances across cosmic spaces, systematic challenges at every level within void environments. Parallax measurements of nearby stars might be affected by gravitational lensing from local dark matter distributions that differ from cosmic norms. Cepheid variable star distances could be systematically biased by metallicity effects resulting from altered chemical evolution in void galaxies. Surface brightness fluctuation measurements might be affected by stellar population differences that emerge from void-specific galactic evolution. These distance measurement biases propagate through astronomical analysis in ways that affect conclusions about fundamental cosmic properties. If cosmic distances are systematically underestimated or overestimated due to void effects, then calculations of luminosity, mass, and energy for cosmic objects become correspondingly incorrect. The apparent brightness of distant galaxies, the inferred masses of galaxy clusters, and even the estimated densities of dark matter and dark energy all depend on accurate distance measurements that our void environment might systematically distort. Gravitational lensing observations, which reveal dark matter distribution through its effects on background galaxy images, face particular challenges within void environments. The reduced dark matter density within our cosmic neighborhood weakens gravitational lensing effects compared to typical cosmic regions, potentially creating systematic biases in measurements of cosmic geometry, dark matter clustering, and the properties of dark energy. Weak lensing surveys that map dark matter distribution across large cosmic volumes must account for environmental effects that vary significantly between void and non-void regions. Dr. Catherine Haymans from Edinburgh University, who leads the kilo-degree survey mapping dark matter through gravitational lensing, explains the measurement challenges. Gravitational lensing is exquisitely sensitive to the total matter distribution along the line of sight between distant galaxies and our telescopes. If we're observing through a cosmic void with reduced matter density, then every lensing measurement contains systematic bias that affects our conclusions about cosmic structure and dark matter properties. The cosmic microwave background, our most ancient observable light, might be systematically affected by our void environment through mechanisms that remain poorly understood. Photons from the cosmic microwave background have traveled through nearly 14 billion years of cosmic space, including the last 2 billion years through our local void. This journey through underdense space might systematically affect temperature measurements in ways that could bias fundamental cosmological parameters, including cosmic curvature, dark matter density, and the properties of primordial fluctuations. Recent theoretical work suggests that cosmic microwave background radiation experiences subtle modifications as it travels through large cosmic voids due to gravitational effects, Thomson scattering by residual electrons, and interactions with magnetic fields that differ from cosmic averages. These effects, while individually small, could accumulate over the vast distances involved in cosmic microwave background propagation to create systematic biases in temperature measurements that exceed current observational precision. Supernova observations face additional systematic challenges beyond simple expansion rate measurements. Type Ia supernova, which serve as standard candles for cosmic distance measurements, might behave differently in void environments where stellar evolution occurs under reduced external pressure and altered chemical abundances. The progenitor stellar populations that create Type Ia supernova evolve differently in cosmic voids, potentially affecting supernova brightness, color evolution, and light curve properties in ways that introduce systematic biases into distance measurements. The stellar initial mass function, the distribution of masses for newly formed stars, might vary between void and non-void environments due to different gas pressures, metallicities, and external radiation fields. Such variations would affect the luminosity evolution of stellar populations, the production rates of heavy elements, and the frequency of various types of stellar explosions. These effects would systematically bias measurements that depend on understanding stellar evolution and nucleosynthesis in different cosmic environments. Perhaps most concerning is the possibility that fundamental constants of nature might vary across cosmic space in ways that become detectable only through precision measurements across cosmic distances. Laboratory measurements sample only tiny cosmic volumes over brief time periods, potentially missing variations that affect cosmic structure and evolution on large scales. If physical constants vary within void environments, then every measurement of cosmic physics might need recalibration to account for local environmental effects. Dr. John Webb from the University of New South Wales has spent decades searching for evidence of varying fundamental constants using observations of distant quasars. His recent analyses suggest subtle variations in the fine structure constant that correlate with cosmic structure in ways that might indicate genuine spatial variation rather than systematic observational effects. If fundamental constants vary across cosmic voids, then physics itself might operate differently in our cosmic neighborhood compared to typical cosmic regions. The systematic nature of these measurement impacts suggests that modern cosmology might be fundamentally biased by our unusual cosmic location in ways that affect every major theoretical conclusion about cosmic evolution, structure formation, and the nature of dark matter and dark energy. Resolving these biases requires understanding void physics with precision that exceeds current theoretical and observational capabilities, creating a circular problem where accurate cosmology requires understanding our void environment, while understanding our void requires accurate cosmological measurements. Recent attempts to address measurement biases through multi-messenger astronomy, combining electromagnetic observations with gravitational waves, neutrinos, and cosmic rays, face similar systematic challenges. Each messenger type might be affected differently by void environments, creating systematic discrepancies between measurement techniques that could either reveal environmental effects or introduce new forms of measurement bias, depending on detailed physics that remains uncertain. The measurement impact crisis has forced astronomers to develop new analysis techniques that can account for systematic environmental effects without requiring detailed theoretical understanding of void physics. Machine learning approaches can identify and potentially correct for systematic biases in observational data, while Bayesian analysis methods can incorporate environmental uncertainties into cosmological parameter estimation. However, these techniques require assumptions about void effects that remain poorly constrained by current observations. The implications extend beyond technical corrections to fundamental questions about the reliability of scientific knowledge obtained from unique observational perspectives. If our cosmic location systematically biases every major measurement we make about the universe, then astronomy faces methodological challenges that require developing new approaches to observation, analysis, and theoretical interpretation that can account for observer bias on cosmic scales. This measurement crisis reveals that our cosmic void discovery represents far more than an interesting astronomical phenomenon. It challenges the empirical foundations of modern cosmology and forces recognition that our scientific understanding of the universe might be fundamentally biased by our extraordinary cosmic address. Chapter 7. Theoretical Challenge. The existence of our cosmic void poses fundamental challenges to theoretical cosmology that extend far beyond simple parameter adjustments or model refinements. Every major theoretical framework that successfully explains cosmic structure formation on smaller scales fails completely when attempting to account for the massive emptiness that surrounds our local group. This systematic theoretical breakdown suggests that our understanding of cosmic evolution remains fundamentally incomplete, despite decades of apparent success in explaining cosmic phenomena. The lambda-CDM model, which serves as the standard framework for modern cosmology, predicts cosmic structure formation through gravitational collapse of dark matter, following patterns established by quantum fluctuations during cosmic inflation. According to these well-tested theories, the largest voids should form when matter flows out of initially underdense regions toward areas destined to become galaxy clusters. However, even starting with the most extreme initial underdensities consistent with cosmic microwave background observations, This evacuation process cannot produce voids larger than roughly 400 million light-years across, less than 1/4 the size of our observed cosmic desert. Dr. Volker Springel from the Max Planck Institute for Astrophysics, whose Millennium simulation represents one of the most sophisticated computational models of cosmic structure formation, acknowledges the theoretical crisis. We can simulate cosmic evolution across billions of years with extraordinary precision, accurately reproducing galaxy formation, cluster evolution, and cosmic web structure on every scale we've tested. But when we apply the same physics to conditions that might produce voids like yours, we consistently fail. Either our understanding of cosmic structure formation is fundamentally incomplete, or your void represents evidence for physics beyond current theoretical frameworks. Inflation theory faces particular challenges from our cosmic void's existence. Standard inflation models predict that quantum fluctuations during the inflationary epoch should produce density variations following specific statistical patterns that can explain the cosmic microwave background's temperature, variations, and the formation of cosmic structure on scales from galaxies to superclusters. However, these same models predict that coherent structures approaching our void's magnitude should be exponentially unlikely, so rare that they shouldn't appear anywhere within the observable universe's finite volume. The statistical mechanics of cosmic structure formation present additional theoretical challenges that push beyond conventional physics into territory that approaches fundamental impossibility. Large-scale cosmic structure emerges through processes analogous to thermodynamic equilibration, where matter redistributes to minimize gravitational potential energy while maximizing entropy. Achieving the extreme underdensity observed in our void would require statistical fluctuations so unlikely that they violate basic assumptions about how random processes operate over cosmic timescales. Dr. George F. Stathu from Cambridge University, whose theoretical work contributed to developing the lambda-CDM model, describes the magnitude of the theoretical challenge. Creating a void like yours requires initial conditions so extreme and subsequent evolution so precisely coordinated that the joint probability approaches what mathematicians call practical impossibility. We're not just talking about unlikely events, we're talking about configurations that shouldn't exist anywhere within cosmic volumes comparable to what we can observe. Dark matter simulations face equally severe problems when attempting to explain our cosmic environment. Unbody computational techniques that accurately reproduce galaxy formation, cluster evolution, and cosmic web structure consistently fail to create voids matching our local emptiness, even when researchers artificially adjust initial conditions to maximize void formation. The largest voids produced by these simulations remain significantly smaller and less perfectly symmetric than observations of our cosmic neighborhood require. The failure extends to dark energy physics as well. While dark energy successfully explains cosmic acceleration on global scales, its behavior within large voids should create observable signatures that differ from what we actually observe. Dark energy's influence becomes more pronounced in underdense regions where gravitational attraction from surrounding matter is reduced, but the detailed predictions for how dark energy should behave within voids like ours don't match observational data, suggesting missing physics in our understanding of cosmic acceleration. Modified gravity theories, which attempt to explain cosmic acceleration without invoking dark energy, encounter similar difficulties when confronted with our void's existence. Whether formulated as FGAR gravity, scalar tensor models, or extra-dimensional scenarios, these alternative theories struggle to reproduce both cosmic acceleration and large void formation simultaneously while remaining consistent with other precision cosmological observations, including cosmic microwave background fluctuations and Big Bang nucleosynthesis. The cosmic homogeneity principle, which assumes that the universe appears roughly uniform when viewed from any location on sufficiently large scales faces fundamental challenges from our void's existence that require either abandoning this foundational assumption or drastically revising what constitutes sufficiently large scales for cosmic homogeneity. If cosmic structure varies dramatically on billion light-year scales, then the universe might be far more complex and heterogeneous than theoretical cosmology assumes. Recent attempts to resolve the theoretical crisis through exotic physics scenarios have created new problems that often exceed the explanatory capacity of conventional scientific frameworks. Theories involving cosmic strings, domain walls, or primordial black holes can potentially affect large-scale structure formation, but they predict observable signatures, gravitational wave backgrounds, cosmic microwave background distortions, galaxy alignment patterns that remain undetected despite increasingly sensitive searches. The possibility that our void represents evidence for physics beyond the standard model of particle physics and general relativity opens theoretical possibilities that extend far beyond conventional cosmology. If cosmic structure formation involves unknown particles, forces, or interactions that become significant only on the largest cosmic scales, then understanding our void might require discoveries in fundamental physics comparable to those that produced quantum mechanics or revealed the existence of dark matter and dark energy. Dr. Sean Carroll from Caltech has explored whether quantum mechanical effects might influence cosmic structure formation on scales previously considered purely classical. His theoretical work suggests that quantum correlations might create large-scale structure patterns under specific conditions that require physics beyond current theoretical understanding. However, these scenarios invoke quantum effects on macroscopic scales that challenge basic assumptions about the relationship between quantum mechanics and classical physics. The anthropic principle offers alternative theoretical approaches that sidestep conventional physics by arguing that we observe cosmic properties compatible with consciousness existence because only such properties allow observers to exist. If complex life requires the stable galactic evolution that void environments provide, then conscious observers would naturally find themselves in cosmic locations like ours, regardless of their statistical likelihood within cosmic structure as a whole. However, even anthropic arguments struggle with the extreme properties of our cosmic void. Detailed calculations suggest that if anthropic selection operated to place observers in optimal cosmic environments, the selected locations would still be far less extreme than our actual cosmic address. Our void appears more empty and stable than necessary for biological evolution, pushing statistical improbability beyond levels that anthropic arguments can reasonably explain. Information theoretic approaches to cosmology suggest that cosmic structure formation might involve computational processes rather than purely physical evolution. If the universe operates as a vast information processing system, then cosmic voids might represent computational artifacts or information storage regions rather than conventional gravitational structures. This possibility connects cosmic evolution to fundamental questions about the relationship between information, computation, and physical reality. The systematic failure of theoretical frameworks to explain our cosmic void suggests that resolving this mystery might require intellectual revolutions comparable to those that produced relativity theory or quantum mechanics. Such revolutions typically emerge when accumulated observational evidence becomes inconsistent with established theoretical paradigms, forcing development of entirely new conceptual frameworks that transcend previous limitations, while preserving successful aspects of earlier theories. The theoretical challenge posed by our cosmic void ultimately forces recognition that our understanding of cosmic structure formation might be approaching fundamental limits that require abandoning cherished assumptions about space, time, matter, and the relationship between physical law and cosmic evolution. This theoretical crisis leads directly to perhaps the most profound implication of our void discovery, what it reveals about the nature of cosmic evolution and our ability to understand cosmic reality from our unique observational perspective. Chapter 8. Comparative Analysis Understanding. Our cosmic void's true significance requires comparing its properties to cosmic structure elsewhere in the universe, an analysis that reveals just how address truly is when viewed against the backdrop of typical cosmic environments. This comparative perspective illuminates not only the uniqueness of our local emptiness, but also what our unusual cosmic neighborhood reveals about the full range of cosmic structure and the conditions that allow complex evolution to occur. The observable universe contains thousands of identified cosmic voids, but none approach our local emptiness in size, spherical symmetry, or degree of underdensity. The Bode's void, previously considered the largest known cosmic emptiness, spans roughly 330 million light-years across and contains remarkably few galaxies for its size. Yet our KBC Void dwarfs even Bode's by factors of 6 in linear dimension and over 200 in total volume, while maintaining even lower average galaxy density throughout its interior. Dr. Rien van de Wegaert from the University of Groningen, whose research group maintains the most comprehensive cosmic void catalog, provides crucial perspective on this comparison. We've identified and characterized thousands of cosmic voids across billions of light-years of space, and your local void stands out as a genuine anomaly. It's not just larger than typical voids, it's larger than our theoretical understanding suggests should be possible anywhere in the observable universe. Most cosmic voids exhibit irregular, elongated shapes reflecting the complex gravitational influences that shape them during cosmic evolution. They typically contain significant internal structure, including galaxy filaments, small clusters, and secondary voids nested within the larger emptiness. Our void, by contrast, maintains remarkable spherical symmetry with smooth boundaries and minimal internal complexity characteristics that make it even more difficult to explain through conventional structure formation processes. The density contrast between our void and typical cosmic environments provides another measure of its extraordinary nature. While cosmic voids typically show galaxy densities reduced to 50 to 70% of cosmic averages, our local emptiness exhibits densities below 20% of cosmic norms throughout most of its volume. This extreme underdensity approaches the theoretical limits for how empty cosmic regions can become through conventional gravitational evacuation processes. Galaxy properties within our void differ systematically from those in typical cosmic environments in ways that reflect the unique evolutionary conditions present within our cosmic desert. Void galaxies tend to be bluer, indicating active star formation. They show higher gas fractions, providing fuel for continued stellar birth. And they display less clustered spatial distributions, reflecting reduced gravitational interactions. The Milky Way and other local group galaxies exhibit these characteristics to extreme degrees that suggest evolution within an unusually stable and underdense environment. Dr. Kelly Hess from Astron has conducted extensive radio observations comparing hydrogen gas content in galaxies across different cosmic environments. Her research reveals that galaxies within large voids maintain gas reservoirs 2 to 3 times larger than similar galaxies in cosmic walls or clusters, allowing continued star formation for extended periods after their counterparts in denser regions have exhausted their fuel supplies. The local group galaxies show gas properties consistent with evolution in the most extreme void environments detected anywhere in cosmic surveys. The cosmic web structure surrounding our void also differs from typical cosmic architecture in ways that enhance our isolation. Most large voids exist near or between major galaxy clusters, creating complex gravitational environments that affect their internal evolution through tidal forces and matter infall. Our void maintains remarkable isolation from major overdensities, with the nearest significant galaxy cluster, Virgo, positioned at the void boundary rather than creating gravitational disturbances throughout the void interior. Comparative analysis of void formation timescales reveals another unusual aspect of our cosmic environment. Most cosmic voids show evidence of ongoing evolution, with matter continuing to flow outward from their centers toward surrounding denser regions. Our void appears to have reached equilibrium roughly 6 billion years ago and remained relatively stable since then, providing consistent environmental conditions throughout the latter half of cosmic history, a stability that proves crucial for successful galactic evolution and biological development. Computer simulations allow detailed comparison between our void and the cosmic structure that develops under typical conditions. The Illustris project, which models galaxy formation across a cosmic volume containing hundreds of voids, reveals that void environments systematically produce galaxies with properties matching those observed in our local group. However, even within this comprehensive simulation, no single void approaches our local emptiness in size or exhibits the perfect spherical symmetry observed in our cosmic neighborhood. The comparative analysis extends to cosmic ray environments, magnetic field properties, and gravitational wave backgrounds that differ between void and non-void regions. Galaxies in dense cosmic environments experience higher cosmic ray fluxes from nearby supernova and active galactic nuclei, stronger magnetic fields from galactic interactions, and enhanced gravitational wave backgrounds from binary mergers. Our void location provides natural shielding from these external influences, creating optimal conditions for stable planetary environments and biological evolution. Dr. Miguel R. Goncalvo from UC Riverside has developed statistical techniques for comparing cosmic environments across large survey volumes. His analysis reveals that our void ranks in the most extreme category for every measured property size: emptiness, symmetry, and isolation from gravitational influences. Finding ourselves positioned within such an unusual cosmic environment represents a statistical coincidence so unlikely that it approaches practical impossibility. The comparison extends to cosmic evolution timescales as well. In typical cosmic environments, galaxies experience frequent interactions, mergers, and tidal disruptions that alter their structure and evolution over cosmic time. Galaxy groups undergo regular encounters with neighboring systems that strip away gas reservoirs and trigger starbursts that exhaust star formation. Materials. Our local group's evolution in cosmic isolation allowed preservation of delicate galactic structures and continued star formation that would have been impossible in typical cosmic neighborhoods. Recent observations from the James Webb Space Telescope allow comparison of galaxy formation across different cosmic environments with unprecedented precision. Early galaxies within void environments show enhanced star formation efficiency, distinctive chemical evolution patterns, and structural properties that differ systematically from galaxies forming in dense cosmic regions. These differences suggest that void environments provide optimal conditions for galaxy formation and evolution that are rare elsewhere in the cosmic web. The comparative analysis of cosmic structure formation reveals that our void represents not just an unusual cosmic configuration, but potentially an optimal environment for the development of complex structure and eventually complex life. The stable gravitational environment, reduced radiation backgrounds, enhanced gas retention, and extended chemical enrichment create conditions that maximize the probability of developing planetary systems capable of supporting biological evolution over cosmic timescales. Perhaps most significantly, the comparison reveals that our void location might represent a necessary rather than accidental condition for the emergence of consciousness. If complex life requires the billion-year stability, reduced external disturbances, and steady chemical enrichment that void environments provide, then Conscious observers would necessarily find themselves in cosmic locations similar to ours, regardless of their statistical rarity within cosmic structure as a whole. This comparative perspective transforms our void from an astronomical curiosity into a crucial component of cosmic architecture that enables the universe to develop the complex structures necessary for life and consciousness. The vast emptiness that surrounds us might represent essential cosmic infrastructure rather than wasted space, the necessary foundation that allows rare regions to develop the sophisticated organization required for awareness to emerge and contemplate its own cosmic context. The comparative analysis ultimately reveals that our cosmic void represents far more than an unusual astronomical structure. It provides optimal conditions for cosmic evolution to achieve its most complex and sophisticated expressions, culminating in the development of consciousness capable of understanding its own cosmic origins and significance.